We're on to class activity 4B on page CA72. Here we're understanding the different types of multiplication word problems that we could pose to our students. And there's three main types that were described in our text and that I would like you to come up with examples for. The first is an array problem. And in an array problem, we have objects that are arranged in a rectangular pattern. So we have rows and columns with an equal number of items in every row and an equal number of items in each column. So I often think of an egg carton when I think of an array problem. We have 2 rows of 6 columns of eggs. Altogether, we have 12 eggs in the carton. An ordered pair problem has several different types that you get into when you're working with more advanced students or students in the middle grades. But for the basic understanding of an ordered pair problem, we have different groups of items, so different classifications. So if I'm making a sandwich, we have different types of bread, different types of meat, different types of cheese. And there's choices in each group. So let's say I have 2 types of bread, 3 types of meat, and 4 different types of cheeses. What are the different combinations I can make where I choose one from every group in order to create a pair or a combination? So in my case, my 2 types of bread can be expanded 3 different ways, and each one of those 3 different ways can be expanded further 4 different ways. So I often think of a tree diagram, which is referenced in your book as well, but the end result is that we have 2 times 3 times 4. It's a multiplicative relationship between the different categories in an ordered pair. So that answer would be 24. And finally, the third type of multiplication word problem that I'd like you to create a sample for is a multiplicative comparison, where we talk about the multiplicative relationship between 2 quantities. So my son Zach is about 3 feet tall. His father's twice as tall as he is. The relationship between them is that Dad is 2 times Zach, or Zach is 1/2 times Dad. Moving along to class activity 4R on C. Here we're looking at the standard and partial products multiplication algorithms. And I must say that I'm a fan of the partial products algorithm, especially as you are scaffolding students to the standard algorithm for multiplication. It more explicitly shows the relationship between the place value of each number and exactly what you're doing. It's also a good stepping stone for the distributive property, which we'll see in just a minute, and later more advanced algebra concepts in the middle grades and beyond. So if we look at the standard algorithm, the way most of us would attack this problem, we'd look to the ones place first. We'd multiply 7 times 5. We'd record a 5 and carry a 3. We'd go on. We know to leave a phantom space underneath the ones place 5 and multiply 7 times 9, which is 63, and add on the 3 that we carried. We'd record a 6 and carry a 6 to the hundreds place. We'd leave 2 phantom spaces in the third line of our algorithm. Multiply 7 times 4, 28, plus 6 more is 34. We'd record that. We'd sum all of the rows of our multiplication algorithm to get the answer of 3,465. The partial products algorithm actually does the same exact math, the same exact calculations. It just more explicitly shows the place value of each of the digits that we're multiplying. So we write a different row for every different multiplication sub-problem that we do. So 7 times 5 is 35. I record 35. There's no carrying, there's no phantom spaces coming up. So it's a lot better for students who have those visual spatial problems, as well as the ones who are just sloppy with their work for whatever reason, whether it's a disability or whether they're just sloppy with their work. The next row of my multiplication algorithm would show that I'm multiplying the 7 with the 9 from 495, which has a value of 90. So 7 times 90 gives me 630. The third row of my algorithm shows that I'm multiplying 7 times the 4 from 495, which has a value of 400. So that results in 2,800. When I sum those 3 steps, I get the same result as if I did it the standard way. However, it's just a lot clearer for students, especially those students who struggle. With a more complex problem, it would look something like this. The important thing to note here is that each one of the factors in my product has more than one digit, so it has more than one place value. So I need to make sure that I get every combination of the place value digits. So I need ones times ones times tens, tens times ones, and tens times tens. And this becomes important and is a good scaffold for the distributive property where we do first, outside, inside, last in later algebra. But it at least exposes students to the idea that when we multiply and we decompose numbers into their tens and ones and multiply it by another decomposed number that's in its tens and ones, there are 2 pairs that we need to find every possible combination for. And again, we're going to get the same result no matter which method we use. Which brings us to class activity 4T on page CA92. And here, this visually shows how we decomposed 45 into 40 plus 5 and 23 into 20 plus 3, and then combined the tens with the tens, that forms the yellow region, the tens of 40, 5, with the ones of 23, that forms the pink region, the tens of the 23 with the ones from the 45, that forms the green region, and then the ones value of each digit, which forms the blue region. And this is a good visual for really making it clear to students exactly what we're doing when we use an algorithm to do multiplication.